All right, we have to get officially introduced now, Malcolm. So Malcolm Risk, who we very, very much begged to speak to us today, is a PhD student in the Department of Biostatistics at the University of Michigan. And I'm fascinated with his topic. His dissertation focuses on federated statistical inference, which he'll describe to us, survival analysis and electronic health records, or EHR. He's also passionate about answering clinical questions about vaccine efficacy and transfusion medicine using EHR data, and has conducted several research projects with hospital networks in Michigan, Florida, and Ontario, towards this end. And Malcolm, thank you again. This is such a modern topic and something that we all need to be aware of. Thank you.
Okay, thanks, Susan, for inviting me, and thanks to everyone for coming. So yeah, as Susan mentioned, today I'm going to talk about non-parametric federated survival analysis, and specifically how we accomplish that through sequential updating algorithms using the influence function. And this is work with both of my advisors, Lily Zhao, who's currently at Northwestern, who's previously a professor at Michigan, and Zhu Shi, who's currently a professor in the Department of Biostatistics here at the University of Michigan. So I'm just going to start with an introduction to a lot of the underlying concepts here, because I think probably this entire field and a lot of the methods we're going to be using are going to be pretty unfamiliar to people, especially since it's something that's really only emerged just in the last 10 years with the advent of really massive electronic health record data. Then I'm going to go through some methods and then just give a few details of simulations and the clinical application for the method I'm talking about today. So federated learning and federated statistical inference. So basically, we always want to be where we can conducting clinical research using multi-center data, especially in the modern era, because the more data that we can use from a broader variety of sites.
Are you sharing your screen?
Yeah. Oh.
We just see you.
Yeah. Gotcha.
Yeah, that's what I was telling Susan. And for all my students, they know exactly
Share.
all that is all.
I would just share.
Forget to switch over.
Yeah. Okay.
There we go.
Okay, good. I didn't get very far at all. Okay, so yeah, today I'm going to be talking about federated learning and federated statistical inference. So the big motivation for this is that we want to be able to conduct clinical research on the largest possible set of data, such that we have maximum generalizability and maximum statistical power. However, in a lot of observational study cases, the data we're working with is electronic health record data, which, unlike clinical trials, we don't generally have a very broad consent process such that we can use people's data and share it freely. Which means that, due to privacy concerns, sharing data across sites is often prohibited, or it's going to require a very onerous and lengthy approval process in terms of REBs and things like that. That's really going to slow down research, which is not something that we want. So I tend to use two different terms here. So federated learning is a really popular term, but that's really come to mean machine learning and computer science methods, where we do prediction modeling using data from multiple sources. And often this doesn't even mean clinical data or hospital data. Often what we're talking about this is trying to train a model based on data from your iPhone, for example, without actually being able to share that data off your iPhone, and using that for entire networks of mobile devices. So as a result, to distinguish our work, which is more in the vein of clinical research, causal inference, and hypothesis testing, I prefer to use the term federated statistical inference, which kind of distinguishes the task we're trying to do here, where we're not only interested in prediction modeling, we're also interested in being able to quantify our uncertainties, give some confidence intervals, and actually test whether medical treatments work.
Could you, I'm sorry, I'm not completely understanding what you mean by only, it sounds like the data only on the iPhone. It's something that you can't link with something else or what? Can you elaborate on that a little?
Right, so the idea is if we have individual level data
Mhm.
on someone's phone, often when, let's say, a company like Apple or Google tries to train a prediction model on iPhones, they're not taking all of your data, moving it to a data center, and then doing all the analysis in one place, because that's really space inefficient. So what they're doing instead is your phone is actually locally doing analysis and helping to update a prediction model. And so this is analogous to
I see.
a case where we want to be able to fit a model using data from multiple hospitals, but we can't actually share people's individual data in some sort of central repository. But yeah, these applications are quite different, so I try to keep them separate in his terminology.
Thank you.
So in terms of what federated statistical inference looks like in practice, there's kind of a variety of types of algorithms that you'll see. One type is centralized algorithms, where one site kind of gets appointed as the central or main site in the analysis, and then it's going to basically be the site that is processing all of the main update steps to the model. So what that means is the central site is going to fit some sort of initial model. It's going to share that initial model with satellite sites. Those satellite sites are going to look at the estimates for that model or whatever summaries have been shared. They're going to basically suggest an update step to the central site based on their data. And then those update steps are going to get aggregated in the central site. We also have these sequential update processes where we have an initial model at the first site that gets passed to the second site. They apply an update step, and that gets passed on the line until all the site's data have been incorporated. Two things about the sequential approach that I would mention is, first of all, there's a really strong analogy here between this and something called online learning, where data arrives in batches. So there's sort of more of a temporal element to it. And yeah, I'd say that's the main thing that I would say about that sequential process. In practice, these methods tend to give a similar flavor of results. But just in terms of model architecture, sometimes people will prefer one or the other. In terms of the methods that I'll talk about today, most of those are going to be sequential methods. So what kind of things get shared when we do federated learning or federated inference? The first thing that always gets shared is the current parameter estimates. So for a regression model, that's going to look like just your standard regression coefficients. For causal inference, that's going to be your nuisance parameters. So you might share regression coefficients for a propensity score model, and then also your current estimate for the average treatment effect. And then for machine learning, this might look like something like weights or an activation function. Now for federated statistical inference, we don't just need to share current parameter estimates. We also need to share a measure of uncertainty. And usually what that looks like is a Hessian matrix or a likelihood. And this is important for two reasons. The first reason is because at the end of the day, we want to do inference. So we're going to need to update some sort of estimate of uncertainty so we can construct something like a confidence interval or do a hypothesis test at the final site. The second reason we need this is we need this to know how large update steps we should be taking at each new step that pushes an update step. And you can think of this basically as analogous to if you're doing some sort of gradient descent algorithm. It's the score that determines the direction you're going in, but the size of that step is going to be determined by the Hessian matrix. And so it's important to be sharing this measure of uncertainty, both for estimation, but also for inference. So now to get into the specific thing that we're going to be trying to do in a federated setting, I'm going to talk about Kaplan-Meier curves. So Kaplan-Meier curves are a form of non-parametric analysis that has been developed for specifically time to event data. What I mean by time to event data is that we're following a cohort of people for a certain period of time, and then some of those people are going to get lost to follow-up. So they're not going to be experiencing the event of interest. So that could be death, that could be infection, that could be any sort of outcome. that happens in a time to event fashion. So some individuals are going to experience an event and some individuals are not going to experience an event. And that calls for some special methods. And so the way that data usually takes shape is for every individual, we have a follow-up time that tells you how long we followed this individual for, and then they'll have a censoring indicator. So if their censoring indicator is 1, that means that they had an event at time xi. If it's 0, it means they didn't have an event. And a Kaplan-Meier curve is just a non-parametric way of estimating the probability of an individual surviving beyond a certain time. And to be honest, I'm not going to get into the details of the math. It's not super important. But basically, every time an individual has an event, at each unique event time, there's going to be a jump downwards in the curve, indicating a reduction in survival probability past that time. We also have confounder adjustment in this model, generally using inverse propensity weighting. So first, we're going to fit a propensity score model. We're going to use that to weight the individuals, and that's going to allow us to adjust for any sort of confounding factors. The last thing I would mention is that in some settings, we would present the cumulative incidence, which is 1 minus the estimated survival probability. So for example, a Kaplan-Meier curve, this is actually presenting the cumulative incidence, so f hat of t, which is just 1 minus the Kaplan-Meier estimator. This is an example from the Moderna COVID-19 vaccine trial. You can see that we have these distinctive jumps each time an individual experienced an event. And you can see that obviously they were able to determine from this that the vaccine was pretty effective because you have this massive increase in probability of having an event in the placebo arm that you don't see in the treatment arm.
Mm-hmm.
So why is federated statistical inference needed for Kaplan-Meier curves? There's a few reasons for this. The first one is that for smaller institutions, sharing a risk table that would look like something like we have at the bottom of this plot. So that's between certain times, the number of individuals who were at risk. So that's the number of individuals that we were still following that far into the study. And also the number of events that occurred during that time. So that's what you see below the plot here. And if you share a detailed enough risk table to actually be able to construct that curve, at least for smaller institutions that are involved in your study, that risk table is always going to identify exact patient survival times. And that's often not something that people are willing to share. This is not always a privacy concern. There's some cases in which that might not be considered identifying data for patients. But in many cases, jurisdictional and institutional policy is going to prohibit sharing this. And then even more importantly, in the case of inverse propensity weighted Kaplan-Meier curves, sharing weights or the covariates that are needed to build the propensity score model is often going to be a privacy concern. And in general, pretty much regardless of whether you can try to convince someone that you should be allowed to share this data, especially in the United States, sharing any amount of data that's of similar dimension to your original data set is always going to raise a lot of questions and probably going to require oversight or approval. So that's why we need to develop some sort of method to construct Kaplan-Meier curves that doesn't require sharing individual level data. And why is this question so difficult? Or why do we have to go to all these lengths to solve the problem, as you'll see soon? So the first thing is that we have an infinite dimensional parameter space. What I mean by this is that the functional number of parameters that we're estimating is the number of jumps in the survival curve. So the complexity of the survival curve is going to grow with the number of events that you observe. What that means is that it's harder to reduce this problem to a fixed set of parameters. So a lot of the existing methods that people have developed for federated inference aren't very effective. The second thing is that we don't really have a clearly defined concept of a score or a Hessian matrix or a likelihood that often makes it easier to share summary statistics and fit these models. And then finally, unlike in machine learning, batch-wise estimation isn't really a natural approach. So it's pretty easy to fit a neural network in a federated setting because neural networks already operate using processing of limited batches of data at a time in order to fit the model. And that makes things very easy in the machine learning case, whereas for something like a Kaplan-Meier curve, if you're doing it the typical way, you really need all of the data to be in the same place in order to construct the curve. So just to introduce the kind of statistical machinery that we're going to be using to solve this problem, I'm going to talk about the influence function of the Kaplan-Meier estimator. And I'm not going to talk at all about any of the mathematical theory about what this is. I think the only way that you should think about this is it's an indication of the direction that we would expect an observation to shift a survival estimate at a particular time if you add a new observation to the data. Another way of saying this is if we knew the data generating mechanism, so we knew all the true parameters that were generating this data, so how long an individual with these covariates, what would be their probability of surviving beyond time t? If we knew all of that things, would this observation be a negative surprise? So that usually means that individual died early or had an early infection. Or would it be a positive surprise? As in, did this individual survive a very long time without experiencing an event? And the influence function, the only thing I'll talk about from a mathematical perspective is that it's divided into two terms here. And the first term you can see, that's that delta I times I of xi less than t divided by y of xi. That first term is accounting for the impact of individuals who had events. So an individual had an event, they're typically going to drag the survival curve down because our estimate of survival probability is going to go lower past that time. Then the second term is the positive impact the individual has bringing up the survival curve because they didn't have an event. So that's what those two terms mean, and that's why you see this kind of structure. So what does the influence function look like in practice? So this is an example for, I generated some simulated survival data, and then I took an individual who experiences an event. So that's why we have delta I equals 1 here at, let's say, 1.6 months. So you can see that for all the times before they experience their event, they're actually driving up that survival curve, right? Because they're making the risk set bigger and they're making the jumps in the curve small. But once they experience an event, you can see they're having a huge negative effect on the survival curve because they're contributing to the proportion of individuals who had events. And this is a distinctive pattern that you'll see if you plot out any individual subject's influence function. This is another individual who experienced an event instead at 18 months. And you can see they have this positive, increasingly positive actually, effect on the survival curve until they experience an event and then they have a negative effect. And this distinctive increasing pattern, that's because of the effect of censoring. So if we were able to follow up all individuals for the entire follow-up, then actually that would just be totally flat. But since we have censoring, the number of individuals who are left in the study is actually decreasing over time, which means that the leverage of one individual is going to be increasing. And so that's why we observe this increase in the influence function, which you can kind of think of as sort of like a residual. And so when fewer individuals are left in the risk set, that means that the leverage or influence of one individual is higher.
Yes, and at the other side, at the beginning, the leverage is higher for the event. Right?
That's true.
So the leverage would be more versus 18 months.
Yeah, that's also the case. So if you have a lower overall estimate of survival probability, then kind of the room you have to move downwards is smaller. That's true, which is kind of, yeah, that's also why you get this pattern of decreasing negative influence. Okay, so a important property of the influence function that we're going to exploit for inference later is that the variance of a survival probability estimate actually has a close relationship with the expectation of the square value of the influence function. Which means that the influence function operates a lot like a jackknife standard error estimate, which means that if you know the influence function, it's really easy to estimate the variance of any sort of statistical estimator. And in a federated setting, this is particularly important because most of the closed form variance expressions that we have for Kaplan-Meier curves or other non-parametric survival estimates, most of those just can't be computed without having all of the data in the same place. And so it's going to be a lot easier to actually share something like a empirical mean of the square value of the influence function that's later going to allow you to do inference at the final site. But I'll go into much more detail on that later in these slides. Okay, so now introducing methods. That was a really long introduction. I think it was important to give people a good idea of the intuition that we're working with here. So our basic idea is we want to use the influence function to update a Kaplan-Meier curve. And as a basic idea, I'll just defend to you that I think this makes a lot of sense because the influence function is kind of like a residual insofar as it reflects the direction we would expect an individual observation to move our existing estimate. What that means is if we can somehow calculate the influence function without reference to prior data, just based on our existing estimates, then we have a good idea of how we should shift our estimates based on data coming in from a new site. And so everything that follows in this presentation is just following through that basic intuitive idea to its logical conclusion. So the Kaplan-Meier estimate has something called a von Mises expansion, which is essentially, you can just think about it as a Taylor expansion that relates the Kaplan-Meier estimate to the true survival probability and the influence function of all the individual observations. Now, we can use this expansion in order to construct an updating equation that I think is very intuitively attractive. So if we subtract the expansions, so if we expand a Kaplan-Meier estimate based on n+1 observations, and we do the same thing for n observations, and we subtract those two. So those are the Sn+1 of t and the Sn of t down here. And then we just move the Sn of t over to the other side. And we do a ton of very annoying algebra. What you get out the end is that our expected value of the estimate based on n+1 observations is just the estimate based on n observations, plus the influence function of that n+1 observation divided by the cumulative sample size so far, which makes sense. We want to add the influence of the new observation, and we want to weight it in proportion to the amount of other observations that are already in the sample. And so what we're going to do is use this basic updating equation in order to fit the Kaplan-Meier curve in a federated set. So the basic structure of our approach is that we're going to construct a spline approximation to the survival curve. So basically a smooth parametric approximation to a Kaplan-Meier curve at the first site. We're going to share the spline parameters with the next site. At each site, we update the survival probabilities by applying a shift based on the average influence function value of the new observations at that site. We're going to refit the spline to the new estimates. And then for each site, we're just going to redo steps 2 to 4 until all sites have been incorporated. So this is a point where if you were being nitpicky, you might ask me, okay, Malcolm, you're doing a spline approximation. Why aren't you just doing parametric estimation anyway? Wouldn't that be much easier? And I think the big advantage of our approach is it really does capture the non-parametric flavor, because even if the first site is relatively small and we can't fit a super complicated spline approximation, in this approach, we can actually make that spline approximation more complicated as we go on. So we can add more knots to the spline, we can add more degrees of freedom, so we get a closer and closer approximation to the true curve. That's not something that you can do if you're using a traditional form of parametric federated estimation to do this, because then you need a fixed Hessian matrix with a fixed number of parameters at the first site. So this is what our method is going to look like in action. I have this little animation here. Hopefully it works. Yeah.
Nice.
So you can see that at the first site, we had a pretty inaccurate approximation, but as we iterated over all of the sites, we got a closer and closer approximation to what the true Kaplan-Meier curve is. And this is just sort of the visual abstract for our algorithm. So I'm going to get you first to look at panel A. That shows the sequential incorporation of data that happens across sites. So you can see that as we go on, as you saw in the animation, we get closer and closer to the true survival curve that we would have When I say true survival curve, I mean the survival curve that we would have if we were able to pool all the individual level data from all the sites together. So we have this initialization at site 1 in panel B, where we have a spline approximation to the initial Kaplan-Meier curve. We have the communication step where we share the parameters of the spline, and then you can see our process for updating the curve at any individual site. So that plot here, where I have old and new, that is the shift based on the average value of the influence function at some relatively dense grid set of grid points that we want to shift the curve, and then that allows us to fit the new spline approximation and get more and more accurate estimates. Okay, so another thing that we wanted to accomplish was covariate adjustment, because we know that electronic health record data is always going to be hopelessly confounded. We know that people who get the treatment is going to be super different from people who get the control, and so we want to be able to implement inverse propensity weighted Kaplan-Meier curves. So in short, what inverse propensity Kaplan-Meier curves do is they weight each individual based on the inverse of the probability of receiving their treatment given their covariance. And this is just a clever way of making sure that in the weighted population, after we've applied these weights, we have covariate balance between the treatment and control groups. And the way that we accomplish this in this setting is we basically just piggyback off of other people's work. So fitting generalized linear models is already a solved problem in federated statistical inference. You can pick your choice of any number of algorithms. And what we're going to do is fit an initial pass where we fit a propensity score model. We're going to share those coefficients with each site. Each site is going to be able to use that to associate a weight with each individual. And that's going to mean that we're going to be able to fit inverse propensity weighted Kaplan-Meier curves. And the way that we do this is actually that is really easy. So this is a little bit imperfect because in practice, we probably shouldn't be taking inverse propensity weights as fixed, even though everyone in their estimation and their inference process currently does that. I have lots of thoughts about that as well, but if I talked about it, I would get really sidetracked. But if we view the weights as fixed, the weighted influence function is actually just the influence function value that we would have multiplied by the weight. And that makes everything really simple. And then in order to conduct inference, we can use the property that I referred to earlier, which is that we just take the empirical mean of the squared value of the influence function and divide it by n. And luckily, it's very, very easy to keep track of a running sum across a series of sites. And so you can do that for some arbitrary number of time points. And you can have a nice Kaplan-Meier curve with the confidence intervals that you would want. Another thing that people really like using is restricted mean survival time. So that's a popular alternative to the cost model for comparing treatment and control arms, where we just compare the area under the curve up to some point tau. And this is particularly popular when the cost proportional hazards assumption is violated in the cost model and has actually been recommended by the FDA now a number of times. And the proportional hazards assumption is basically never true. So as far as I'm concerned, you should always use this. So basically what this is we're just taking the area under the survival curve. So as we have an estimate for the survival curve based on our spline, it's going to be easy for us to use numerical integration to get the area under that curve up to a certain time tau. It's also the case that we have an influence function for the restricted mean survival time, which actually turns out to just be the integral of the influence function of the survival curve. And so that's something that we can estimate basically just using the trapezoid method based on the influence function values that we already calculated for those individuals in order to update the curve. And then inference is going to follow relatively easily based on the earlier principles. And the final result of this is that we're going to be able to calculate a confidence interval for the ATE. So the difference between the restricted mean survival time in the treatment group and the restricted mean survival time in the control group, which is really nice and is often something that drug companies would want to use for hypothesis testing to figure out whether their drugs actually work.
So Malcolm, in my back brain or my frontal lobe, whichever you prefer, I've been thinking about your fixed weight issue. Couldn't you bootstrap the influence functions?
Bootstrapping is very annoying in a federated setting
It is.
because if you think about it, each site needs to run a bootstrap. And then if it's 500 bootstrap repeats, that means there's 500 separate bootstrap models, which means you have to run the process about 500 times. And so not only is that computationally intensive, it's not very communication efficient. So in theory, that's a solution. It's something that my advisor, Lily, has suggested to me is workable, but I'm more skeptical.
I have this feeling that within Site, you could come up with a bootstrap variance for their part and then do like a bootstrap variance averaged, average
So you think
across the
individuals-
discrete number of sites, right?
Right, so you think individual sites should be able to get their own kind of bootstrap variance, and then
And then
that's an
you
interesting idea.
And then you should be able to kind of combine them, because it's conditional on site times the probability of that contribution coming from the site. And
That sounds plausible. There's another method you can use, which is stack score estimation, which I've done some work on, but that's a bit of a sidetrack as well. And has its own issues as well, even relative to the bootstrap method. Okay, so one more thing I want to mention. So that was kind of the first chapter of my dissertation. In the second chapter, we talk a bit about competing risks. So competing risks is just the same as ordinary survival, but it's when we have people experiencing events, infection or death due to multiple causes. So you might have infection or cancer, let's say, increasing cancer stage with competing risk of death. And so all this means is that our indicator variable, instead of being restricted to 0 or 1, goes from 0 up to k, where there's k minus 1 possible causes of the event that we're worried about or possible competing risks. And in this case, talking about the survival function doesn't make so much sense. So we do non-parametric estimation of cumulative incidence. And this can be done using like a Kelp-Beach-Prentice estimator is what one of them is called, or an Aalen-Johansen estimator. And you could also use inverse propensity weighting to do covariate adjustment for this. And I'm not going to go into huge detail here. All I'm going to say is that we have an influence function for the Aalen-Johansen estimator. This allows us to essentially plug and play the same approach we had for the Kaplan-Meier estimator. I'm going to note here that the influence function for this competing risks cumulative incidence actually depends on the influence function for the ordinary Kaplan-Meier curve. And so we're going to have to use our original model first to estimate the survival curve and the influence function values for that. And then we're going to be able to estimate cumulative incidence for each of the competing risks. And then we also have a measure called restricted mean time loss, which is basically the reverse of restricted mean survival time. So generally you want that number to be lower instead of higher. And that represents the amount of survival time, that's the area under the cumulative incidence curve. And it represents the amount of survival time lost before tau, specifically to that cause k. So it has kind of the opposite interpretation of RMST. And so we're also able to basically do the same algorithm for competing risks. I won't go into any detail on that really. In terms of simulation results, I think simulations are kind of boring. I never like talking about them in presentations. Basically, we have similar bias or almost identical bias, and we achieve the same coverage with our confidence intervals using our distributed method to the method where we could hypothetically pool the data and just construct a normal Kaplan-Meier curve. And I have similar simulation results that also look very nice. This is actually for restricted mean time loss in the competing risk case. And you can see I've separated this out into restricted mean time loss due to death. And since this is simulated data, restricted mean time loss for your choice of events. So that could be infection, or it could be cancer, or something like that.
Are you noticing any difference between the federated and pooled? Anything?
Sometimes when the sample size is small, the
The total sample size or the batch at
The
one
total
site?
sample size.
Okay.
Sometimes when the total sample size is small, you'll actually see over coverage in terms of the spline, the federated model. And that's just because we can't add enough complexity to the spline just because the sample size is smaller. And so we have a bit more parametric smoothing.
It's not an appropriate use of the federated in that
Right,
sense.
yeah, you're gonna want to be using it when the global sample size is very large, like rare events cases where we really need this approach. But otherwise, it looks very similar. I still have some concerns about the coverage and competing risk. You can't really see it there, you know, these plots look really nice, but we're down by about 1%. So we could make some improvements there. Okay, so the application that we chose for this is we use data from 3 separate healthcare centers in Michigan. That's Michigan Medicine, Cornwall Health West, and Cornwall Health East. And as you can see, we did this a while ago. So it was when everyone really still cared about COVID-19 vaccination a lot, which is not so much the case anymore. So we're definitely pivoting to other applications. But we basically had 2 research questions, mostly around adverse events relating to COVID-19 and COVID-19 vaccination. So first of all, comparing the 2 vaccines in terms of whether there were higher incidence of blood clots following one vaccine or the other, but also checking whether incidence of blood clots following first and second dose COVID-19 vaccination was higher for individuals who had an infection or individuals who got the vaccine. Because what we saw with a lot of adverse events is that there were similar adverse events for the vaccine and for the infection, but the adverse events associated with infection were far, far more severe and far more common. And that was basically supported by our analysis. So this was our comparison of cumulative incidence of thromboembolic events, so blood clots for first dose COVID-19 vaccine recipients compared to individuals with SARS-CoV-2 infections. As you can see, there's a massive difference, and it actually tends to get larger when we control for patient covariates. That tends to be because vaccine recipients were much older than vaccine hesitant individuals. So that was the explanation for that. In terms of the comparison between the 2 vaccines, there was a pretty large difference, again, due to age between the 2 vaccines based on when they were rolled out. But you can see things are really very similar. It's actually statistically significant given our massive sample size. But you can see that things were basically super similar between the 2 vaccines. So I'm going to go to conclusions here. I had a little more that I was going to talk about, but I think I prefer to keep it relatively short and leave lots of time for questions. But if you're curious about how this connects to pseudo observations, feel free to ask me about that. Anyway, in terms of conclusions, an effective method for conducting non-parametric distributed survival analysis for visualization and for inference. We have this novel methodological approach of using the influence function that might have wider application outside survival analysis. And we generally support other findings indicating that the protection of COVID-19 vaccines against COVID-19 associated blood clots likely outweighs the risk of any directly induced adverse events. And we actually ourselves had a follow-up study where we did a mediation analysis of this to confirm some of our conclusions. And I've included here, if we're going to share the slides afterwards, I've included here a link to the preprint and my GitHub code. Thanks everyone for listening.
Thank you.
So, as a guess, is a pseudo observation in this setting the influence function for that person? Does it reduce to that?
Yeah, so thank you for so yeah, basically the reason that pseudo observation regression works for people who aren't aware, it's a popular way of conducting survival analysis where we assign each individual, instead of their follow-up time and their censoring indicator, we assign them a pseudo observation outcome, which kind of reflects their impact on the survival probability at a particular time. And the reason this works is just because of that equation there, basically. So the pseudo observation is basically the true value of the survival function, or approximates the true value of the survival function plus the influence function. And that's what all the asymptotic theory of pseudo observations is built off of. And so we actually had, the last thing I'll mention on this, not to indulge myself too much, is that we actually have some work where we showed that you get more accurate pseudo values or more useful pseudo values if you're in a federated setting based on sharing the influence function and allowing each site to use the influence function to compute the pseudo observations rather than just trying to compute those pseudo observations locally. And so that was kind of our trick. And our idea is basically that you calculate this global influence function, and then you can calculate pseudo observations at each site, and then use your preferred federated regression or machine learning framework to fit a model using pseudo observations. Some people think this isn't really a problem, just because they think they can share the risk table and like that's enough to assuage privacy concerns. But I still think it's a nice result.
This is extremely cool. And I think that one of the nice things to connecting it through the pseudo observations is that you can basically move to regression settings from that point. So even though you built all this up in the non-parametric setting, you'll be able to move it into models, I believe.
Yeah.
Do you agree?
I agree. And that makes the federated task a little bit easier because there's so many existing methods for estimating your more standard regressions. And then machine learning is just super easy in a federated setting because it already gets fit batch-wise.
That's very cool. All right. I am so lucky I've never had to worry about keeping secrets with the data across sites. I've been very, very lucky. But this is becoming more and more of an issue. So,
By the way, there's a presentation at ISR several years ago on identity matching, identifying people and items. And it was far more sophisticated than I had thought. So it's one of those fields that's advancing quite rapidly. And if you're not aware of it, you don't realize how advanced it is. So the data privacy problem is just skyrocketing.
I had a question on how this is how it's performed in practice. Did you sign a non-confidentiality agreement with each place, run their batch data, and then not share? And then, because otherwise you need to have computation done in that site, and then computation done on the second site, then computation done on the third site. So how does it get done in practice?
Yeah, I think that tends to be tricky. Like when I've done it in practice, it's only with 3 or 4 sites, and we've had analysts that we've been working really closely with at the other sites. Obviously, if you're trying to do this in a broader setting, I'm running into some issues with the application for my competing risk thing because I'm working with an analyst who has access to the data and I don't have access to the data, and so that makes debugging super inconvenient if you run into any problems. I have been doing some work actually, so I'm from Canada with a Canadian database who really wants to use a lot of federated learning. And I think their idea and my idea as well is that in the long term, I think you would want some sort of more standardized kind of almost web application type of extremely user-friendly, easy experience. So we don't require dedicated analysts who really understand the method at each site.
So perhaps microanalysis on the phone is or analogous to that, batch at the site doing some, and then super batching with anonymization. All right, I see. Yeah, thanks.
other questions from the friend group in the back here?
Do you find culturally or across the globally, you think there's differences for, desires for federated versus sharing data?
Yeah, actually, it was funny. I ran into, one thing is that American privacy law is really strict. So I'm working with this Canadian hospital database, and the number of, I think this is probably just the litigiousness of American society or the influence of lawyers. But the number of firewalls built up or the number of restrictions on your interaction with data as an analyst is much stricter in the US, I would say.
Wow. You really run into that then. Interesting. Huh.
Okay, I'm sensing an end to the question period. So there's still leftover pizza, I think. If you're here in person, you can grab some. Otherwise, let's just thank Malcolm once again. Make him feel welcome. This way, they were for me.